Hello, everybody, and welcome back to another lecture in Geography 341, Weather and Society. I'm just Dr. Zach Hilgendorf, and today we're going to be going further from what we were talking about last time, about kind of water and its function on the planet. We're going to be talking about humidity indices. And we've talked about a few of these definitions at the start of the semester, just so you could get a better idea regarding your weather journal, what these different terms mean. So let's go ahead and roll into it. So as I mentioned, in the last lecture, we talked about the physical and chemical properties of water. Why is that important? Well, if we think of particularly how water exchanges energy and heat, we think of those latent heat exchanges or the exchanges of energy and heat that occur when water is changing from a solid to a liquid to a gas and any variation therein. We're releasing energy or absorbing energy. As we release energy, we're heating up. As we absorb energy, we're cooling down. But with humidity, a lot of times we're thinking about, is it saturated? Is it unsaturated? How much water content is in the air? And we think of water in the air like we see these nice wispy clouds here. There's a mix of a few different types that we won't get into just yet. But we think of water in the air as clouds. So the more humid the air, a lot of times we see cloud formation in the skies, or we feel that expressed as kind of what we would call mugginess on a hot July or August day, right? Where the humidity is 80% humidity and we've got 85-degree Fahrenheit day. And we feel that as kind of a heat index, right? As we're feeling uncomfortable because of the humidity and the content of, or in the heat within the air. So we're interested in the humidity as a property. So the first one that we're going to talk about is of our humidity indices is specific humidity. Simply put, this is the mass of water vapor per unit mass of air, including the water vapor. So we express this in grams per kilogram. This kind of ties into the next one, mixing ratio, the mass of water vapor and a unit mass of dry air. So if we bring these all together and kind of think about them a little bit further, we have a vapor pressure. This is the part of the total atmospheric pressure attributable to its water vapor content. We express this in millibars. Air pressure, as we recall, is just force per unit area exerted on randomly moving gas molecules bouncing off of a surface. Like so. So if we consider specific humidity, mixing ratio, vapor pressure, we can consider relative humidity. That's just the ratio of actual water vapor content in the air to what the vapor content would be if air were saturated at that given temperature. So basically, that's how we often see expressed. It's 80% humidity. That means that the air is holding 80% of the moisture that it could hold if the air were saturated. If it got up to that 100%, then you'd have saturation. Typically, we see that obviously during precipitation events. What does saturation mean? Well, saturation or saturated air is just a humidity state that exists when the rate of evaporation from and the rate of condensation onto a flat water surface is equal. Pretty simple. It just says that the rate of condensation or water condensing and the rate of water evaporating, so gas to a liquid, condensation, liquid to a gas, evaporation, are equal. That's what saturation is, and it's kind of pure sense. So if we were to take an example here, we have our little table with a flat surface of water, and we're going to encapsulate that in a nice little bubble here, just so that we can look at the pressure. If we are heating, you see that little red strip down there, we're heating this water. It's at 10 degrees Celsius. If we were to uncover it, water would evaporate out and that pressure would kind of equalize into our atmosphere or into our little mock atmosphere here in our little bubble. And that would respond, or the pressure would increase, basically. Now, of course, there's also water condensing back onto the surface. So kind of increasing here. So we're adding more and more and more to, so we're evaporating it off of our surface, condensing it in, we're kind of increasing that humidity. We increase the pressure even more. And say we have a saturation vapor pressure of 12.3 millibars, for example, for that 10 degrees Celsius. Sorry, didn't mean for the white screen to pop up there. Now, if this water was heated to 20 degrees Celsius, it's going to increase the moisture content within the air as we're heating it, as it's evaporating off. We're also going to increase the amount of water condensing back onto the surface here in this kind of closed little system here. With 20 degrees Celsius, we would have a saturation vapor pressure of 23.4 millibars, pardon me. So we could look at this. What does that actually look like on a graph form? It's a pretty consistent relationship here. So we've got saturation vapor pressure on the y-axis. X-axis is just temperature, or horizontal axis. So we're going from negative 20 degrees Celsius to negative 4 or to positive 40 degrees Celsius on the horizontal axis. Just below zero vapor pressure to 80 millibars of vapor pressure on the vertical axis. We're going to look here really quick before we kind of dive into our example, because as water is super cooled, you can see here's the freezing point of water right here. We are in degrees Celsius, so this is also equal to 32 degrees F. Right? There, as water is super cooled, if it's not allowed to freeze, things like high pressure, saline content, things like that can create or can make water not freeze solid and stay in its liquid form. We see this kind of separation occurring. So you can see our super cooled water versus ice there. There's a little bit of a difference. So if we were to look at negative 10 degrees Celsius, it's got to be different for example, for saturation vapor pressure of 2.9 for supercooled water or 2.6 for ice. So just note that if you're below 0 degrees and you're looking at saturation vapor pressure, there is a slight deviation therein. So let's have a nice little example here. So what's the relative humidity? And remember the relative humidity, well, we'll show you the equation here in just a second. When temperature is equal to 30 degrees and your vapor pressure is equal to 30 millibars. So recall, relative humidity is just vapor pressure divided by your saturation vapor pressure. So if we know that we look at the percent humidity, just multiply that up by 100. So if we were at 30 degrees Celsius, our vapor pressure, our saturation vapor pressure, is actually somewhere around, say, 42 millibars, or 42 and a half millibars. Whereas the vapor pressure, the actual vapor pressure that we're measuring right now, is only 30 millibars. Simply, just divide them out. 30 divided by 42.5 gives us 0.706 or 70.6% is our relative humidity. If we were to do the same thing, but we had 5 degrees cooler, so click through this here real quick. Our vapor pressure, or saturation vapor pressure there is going to be 31.7 millibars for our temperature, but our relative humidity is, or our vapor pressure is quoted as 30 millibars. So there we've got a much higher relative humidity. We're actually at 94.6 in our relative humidity. So the next one that we're interested in, you often hear this a lot, is the term dew point. And this is just the temperature at which air, given its vapor pressure, would be saturated. The further apart, if we think of it, the temperature is from the dew point, the drier we feel, the drier that air feels. So you can have wildly different temperature dew point. That just means that your relative humidity is much, much, much lower. The closer the temperature and the dew point are to one another, the closer you are to that saturation point. So let's look at that graph again here and say, okay, what's the dew point of this air when our temperature equals 30, our vapor pressure equals 30 millibars? If our vapor pressure is equal to 30 millibars, that means our dew point is somewhere right around here. Dew point's 24 degrees Celsius. Same thing here. Temperature equals 25 degrees Celsius. Vapor pressure equals 30 millibars. Same thing. Dew point's 24 degrees Celsius. All right, so you'll have some of these equations on your quiz. Just note that vapor pressure, if your vapor pressure is kind of dictating your dew point, your temperature is dictating your saturation vapor pressure. So that's the difference. So dew point would give you your vapor pressure. Saturation vapor pressure gives you your temperature. And that's how you can kind of find and work between these. It's kind of just a basic algebraic equation to kind of figure this out here. Okay, so what is the vapor pressure of a parcel of air where temperature equals 25 degrees Celsius and our dew point equals 15 degrees Celsius? Well, dew point, vapor pressure are related, right? If you know the dew point, you can find the vapor pressure. If you know the vapor pressure, you can find the dew point. We go across, we're looking at a vapor pressure of 17 millibars. Likewise, if we know the air temperature, we know the saturation vapor pressure. If we know the saturation vapor pressure, we can find the air temperature. So if we wanted to, for example, find the relative humidity of this air parcel, all we need is the temperature and the dew point, or the vapor pressure or the saturation vapor pressure, or just one from each of them. And we can figure out that, go up on our above 25 where it crosses the line, go over. We're looking at a saturation vapor pressure of 31.7 millibars, and that gives us a relative humidity, if you'll do the math out there, of 53.6%. What's the vapor pressure of this air parcel then, where you've got temperature equal to 25 degrees or 20 degrees Celsius, 5 degrees cooler than our last example. Dew point is held constant at 15. Well, we know vapor pressure, that's going to be 17, just like the last time. Here, we'll go across. That gives us 23.4 millibars. If you divide 17 by 23.4, multiply it by 100, that gives you about, I think it's like 72.6 degree, or 72.6%. So that's our relative humidity of this parcel of air. So again, if you know one, or you know one from temperature and one from dew point, you know the saturation vapor pressure or the pressure, you can find what that relative humidity is going to be. And that's how it's figured out whenever you see it expressed in your weather readouts, for example. Now, it's worth noting that humidity indices are not stagnant. They change and vary throughout the day. If we're going to look at this temperature readout, so the red line here is temperature. This temperature readout at the Eau Claire Regional Airport, this is from September 29th of 2012, just a single day readout from midnight to midnight. We see what you would expect. Temperature decreases until we get to right around 7 o'clock or so in the morning. As we notice, or as we recall, where that's kind of the lowest point of the long wave radiation coming out of the Earth before the sun starts to warm and we start to have that incoming solar radiation warming the surface of our planet again, where we are in the circle of illumination, or the lit part of the world. And then it increases for a while. Sometime around 4 here, we see our maximum, where that's the maximum rate of long wave radiation emitted from the surface of our planet before it starts to drop off again. Great. Now, what does that look like if you're going to look at dew point? Well, we can see here kind of a, relatively speaking, once it gets hot enough, kind of an inverse relationship. But while it's cooler, we're kind of following along that same trend, right? We see it's holding steady at around 4 degrees. Bumps mid-morning, your early parts of the morning, very close. So a lot of times you'll see dew or frost or things like that in the early parts of the morning because we're really close. You're getting some condensation, or you are getting, you're right at that crossing point there to separation or saturation. So you could be getting things like condensation and dew on your grass. And then it kind of dips and decreases as your temperature is increasing, as you're warming. So you're here in this example, it's much drier. If we're looking at, for example, 4 here, 4 in the afternoon or 1600, we can look, that's at about, well, I'd say about 1 degree Celsius. And then for the dew point, so dew point is equal to 1 degree Celsius. Here, our temperature looks like it got up to about 26.8 or so degrees Celsius. So you could figure that out if you wanted. If you could go back to your graph, you could figure out what the relative humidity was at any given point because we know the air temperature, we know the dew point. Now, if we look at relative humidity, because all you're doing is, calculating these things out, it does exactly that. We see it peaking in the morning, right around 90% relative humidity, dropping off substantially as the day warms. So you're having a increasing distance between your, an increasing gap between your dew point and your your air temperature. So your relative humidity is decreasing, and then as the surface starts to cool again, that relative humidity is increasing because your air temperature is decreasing again, getting closer and closer to your dew point. So that's just to look at kind of one cycle in our world here. Speaking of our world, we can look at the dew point climatology of the conterminous United States. Uh, Obviously, conterminous, we're not looking at Hawaii and Alaska in this map. So average dew points in January and July are what we're looking at here. Where we are, we're looking at right around here or so, right? I'll draw it out on both of these here. Right about there on both of them. So in January, we're looking at our average dew points are somewhere below negative 6.7 degrees Celsius. And our in July, they're somewhere around, it looks like 12.8 to 15.6 degrees Celsius. So we can see how much that changes throughout the year. Those are just averages based off of the climate in the United States. So depending on the temperature, that can mean that you've got dry air or you've got very moist air. If we were to look at other places in the United States, we're looking at New Orleans, for example. New Orleans, right about here or so. We'll draw it on both here. New Orleans, we're looking at over 21.1 degrees Celsius and somewhere between, well, that'd be about 4.4 to 10 degrees Celsius in the January. So very, very moist air coming from the kind of the Gulf of Mexico during the warmer months, the summer months. Can be a bit cooler, still moist because your temperatures are dropping as well. But you can see how low that drops during the winter months. Now, if we were to look at average dew points for another place that I've lived, for example, Phoenix. So Phoenix is right about here and right about here, more or less. We can see that in January, right around negative 6.7 to negative 1.1 degrees Celsius. And then in July, somewhere around still negative 1.1 to 4.4 degrees Celsius, or maybe 4.4 to 10. Air in Phoenix during the summer months is incredibly dry. Now it is in the winter months too, but we do see kind of a bump in precipitation. There's kind of a bimodal precipitation trend from the monsoonal period in June to July, and then again in kind of December to February, we see another increase in precipitation. So there, we would actually see much more moist air uh, during the winter months, and then much drier air during the summer months. Now, if you think of the way people describe the desert Southwest, oh, it's a dry heat. That's what they're talking about. It's a dry heat because the dew point is so low relative to the air temperature, and what we feel that expressed as is very dry conditions because we have a low relative humidity. So to recap, we talked about humidity indices, saturation, and how we calculate vapor pressure, saturation, vapor pressure, and relative humidity. In the next ones, we're going to talk about air parcels and how they move and migrate across the world. So stay tuned. We will see you in the next video, and I hope you have a great day. Thanks.